And I hope you guessed function A. Even though both perfectly describe the data, B is much more complex than A. In fact, outside the data, B seems to go to minus infinity much faster than these data points, and to plus infinity much faster than these data points over here. And in between, B has wild oscillations that don't correspond to any data. So I would argue A is preferable. The reason why I asked this quiz is because of something called Occam's razor. Occam can be spelled in many different ways. And what Occam says is that everything else being equal, choose the less complex hypothesis. Now in practice, there's actually a trade-off between really good data fit and low complexity. Let me illustrate this to you by a hypothetical example. Consider the following graph with the horizontal axis graphs complexity of the solution. For example, if you use polynomials, this might be a high degree polynomial over here and maybe a linear function over here, which is a low degree polynomial. The training data error tends to go like this. The more complex a hypothesis you allow, the more you can just fit your data. However, in reality, your generalization error on unknown data tends to go like this. It is the sum of the training data error and another function, which is called the overfitting error. Not surprisingly, the best complexity is attained where the generalization error is minimum. There are sometimes methods to calculate the overfitting error. They go into a statistical field under the name bias variance methods. However, in practice, you're often just given the training data error. You find if you don't find the model that minimizes the training data error, but instead push back on complexity, your algorithm tends to perform better. And that is something we will study a little bit in this class. However, this slide is really important for anybody doing machine learning in practice. If you deal with data and you have ways to fit your data, be aware that overfitting is a major source of poor performance of a machine learning algorithm. And I'll give you examples in just 1 second. So a really important example of machine learning is spam detection. We all get way too much email, and a good number of those are spam. Here are 3 examples of email. Dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly unconfidential and top secret. This is likely spam. Here's another one in upper caps. 99 million email addresses for only $99. This is very likely spam. And here's another one. Oh, I know it's blatantly OT, but I'm beginning to go insane. Had an old Dell Dimension XPS sitting in my corner and decided to put it to use, and so on and so on. Now this is likely not spam. How can a computer program distinguish between spam and not spam? Let's use it as an example to talk about machine learning for discrimination using Bayes networks. In spam detection, we get an email and we wish to categorize it either as spam, in which case we don't even show it to the reader, or what we call ham, which is a technical word for an email worth passing on to the person reading the email. So the function over here is the function we're trying to learn. Most spam filters use human input. When you go through your email, you have a button called is spam, which allows you as a user to flag spam. And occasionally, you'll say an email is spam. If you look at this, you have a typical supervised machine learning situation where the input is an email and the output is whether you flag it as spam, or if you don't flag it, we just think it's ham. Now, to make this amenable to a machine learning algorithm, we have to talk about how to represent emails. They're all using different words and different characters. They might have different graphics included. Let's pick a representation that's easy to process. And this representation is often called bag of words. Bag of words is a representation of a document It just counts the frequency of words. If I even were to say hello, I will say hello. The bag of words representation is the following. 2111 for the dictionary that contains the 4 words hello, I will say. Now look at the subtlety here. Rather than representing each individual word, we have a count of each word, and the count is oblivious to the order in which the words were stated. A bag of words representation relative to a fixed dictionary represents the counts of each word relative to the words in the dictionary. If you were to use a different dictionary, like hello and goodbye, our counts would be 2 and 0. However, in most cases, we make sure that all the words found in messages are actually included in the dictionary. So the dictionary might be very, very large. Let me make up an artificial example of a few spam and a few ham messages. Offer is secret. Click secret link. Secret sports link. Obviously, those are contrived, and I try to retain the vocabulary to a small number of words to make this example workable. In practice, we need thousands of such messages to get good information. Play sports today. Went play sports. Secret sports event. Sport is today. Sport costs money. My first quiz is, what is the size of the vocabulary that contains all words in these messages? Please enter the value into this box over here. Well, let's count. Offer is secret. Click. Secret occurs over here already, so we don't have to count it twice. Link. Sports. Play today, went, event, costs money. So the answer is 12. There's 12 different words contained in these 8 messages.